Alright, in the next few videos we're going to talk about periodic trends. This is a high yield topic for the MCAT, so you'll definitely want to make sure you understand these topics well. The first trend we're going to talk about is the electrostatic force. This is the most important trend, and that's because we use this trend to explain all of our other trends. Now, the equation for the electrostatic force is given by Coulomb's law. We can see here that it's equal to K Q1 Q2 over R squared. In this equation, K is just a constant, Q1 and Q2 refer to the two charges interacting with each other, and R is the distance between the charges. Within an atom, you have negatively charged electrons and you have the positively charged nucleus. These two charges are going to be interacting with each other, and since they're opposite charges, they're going to experience an attractive electrostatic force. Now, the nucleus exerts an attractive electrostatic force on all of the electrons within an atom, but turns out we're not interested in all of those interactions. And that's because we can classify electrons as two types: valence electrons and core electrons. Valence electrons are the electrons in the outermost shell of the atom. They are important because they participate in chemical bonds and chemical reactions. Core electrons are all non-valence electrons, and generally they're less important. So, as you can guess, we're interested more specifically in the attractive electrostatic interaction between the nucleus and the valence electrons, since how tightly the nucleus holds onto the valence electrons is going to determine the reactivity of the different atoms. Now, as it turns out, the valence electrons don't feel the full positive charge of the nucleus, and that's because the core electrons provide a shielding effect. The way to think about it is valence electrons are on the outside of the atom, the nucleus is on the very center. Core electrons are in between them, so essentially the core electrons are shielding the valence electrons from the full positive charge of the nucleus. Now, we can write an expression for this interaction between the nucleus and the valence electrons, and we've done that right here as a proportion, essentially leaving out K as a constant. It looks slightly different because we have E and ZF, but this is just us specifying what the charges are in the interaction. So here, E is simply the charge of an electron. In this case, we're of course talking about the valence electrons, but all electrons have the same charge, so it doesn't really matter what we use. Z effective, this is a new term. This is called the effective nuclear charge. You'll recall that Z by itself is the nuclear charge, and it's equal to the number of protons. The effective nuclear charge is the nuclear charge felt by the valence electrons. It's definitely going to depend on the number of protons in the nucleus. However, as we mentioned earlier, the valence electrons don't feel the full positive charge of the nucleus because of the shielding provided by the core electrons between them. So to calculate the effective nuclear charge, you can take the number of protons in the atom and subtract the number of core electrons. Okay. Now the last term we have here is R, and again we can specify what this is referring to. In this case, it's specifically going to be the distance between the nucleus and the valence shell, where our valence electrons are located. Alright, so let's go ahead and take a look at a few examples of how to do calculations for the effective nuclear charge. And in doing so, we'll also figure out what is the periodic trend for the effective nuclear charge. So we'll look at a couple situations. The first is, let's look at what happens to the effective nuclear charge along a row. So as we go from left to right across a row, what happens to the effective nuclear charge? And we can consider as examples carbon, nitrogen, and oxygen. 3 elements on the same row of the periodic table. And we want to calculate the effective nuclear charge for all 3 of these species. And just following our equation, we can start with carbon. Carbon, we can see on the periodic table, it's got an atomic number of 6. So it has 6 protons, and we want to subtract the number of core electrons. To figure that out, you need to look at the location of the atom on the periodic table. Carbon is located on the second row of the periodic table. That means that carbon has electrons in the first and second shells. Between these two shells, the second shell is the valence shell. So that means the electrons in the first shell are the core electrons. And since there are only 2 electrons in the first shell, we can subtract 2 to figure out that carbon has an effective nuclear charge of +4. We can do the same thing for nitrogen. If you look at the periodic table, you'll see that nitrogen has an atomic number of 7. Again, since nitrogen is located on the second row of the periodic table, it also has 2 core electrons in that first shell. So nitrogen has an effective nuclear charge of +5. Finally, we can take a look at oxygen. Oxygen has 8 protons. It's also in the second row, so it's got 2 core electrons, so an effective nuclear charge of +6. So we look at what happens as we go from left to right across the periodic table, we can actually see that our effective nuclear charge increases. And the reason why it's increasing is because we're adding more protons to our nucleus, but we're not changing the number of core electrons. So we can say along a row, we have an increase in the effective nuclear charge. So now let's look at a column. So along a column, again, we can look at a few examples. Let's say we look at lithium, sodium, and potassium. Again, just follow our equation to calculate the effective nuclear charge. We can see that lithium is on the second row. It's got 3 protons, and again, it's got 2 core electrons in that first shell, so it has an effective nuclear charge of +1. Sodium is going to be slightly different. Sodium, we can see it has 11 protons by its atomic number. We can see that sodium is located on the third row of the periodic table. That means that sodium has electrons in the first shell, the second shell, and the third shell. Between those 3 shells, the valence shell is going to be the third shell. So that means sodium has core electrons in the first and second shell. And the first shell has 2 electrons, the second shell has 8, so that means sodium has 10 core electrons, so an effective nuclear charge of +1. So finally, we can look at potassium. It's got an atomic number of 19. Potassium is located on the 4th row of the periodic table, so it has electrons in the first 4 shells. The 4th shell is going to be the valence shell, so all of the electrons in the first 3 shells are going to be core electrons. And potassium has 18 electrons in those first 3 shells, so it also has an effective nuclear charge of +1. So we can actually see here that the effective nuclear charge does not change along a column. And the reason why it doesn't change is because as you go down a column, you're adding protons to the nucleus, but you're also adding core electrons in equal numbers. So overall, along a column, the effective nuclear charge stays the same. All right. Now, it's important to note that while you go down a column, effective nuclear charge doesn't change. There is something that changes. And that is, when you go down a column, you're adding your electrons to valence shells that are getting progressively farther away from the nucleus. So as you go down a column, the distance between the nucleus and the valence shell is increasing, and that's certainly going to affect our electrostatic force periodic trend. All right, so let's try to put them together, figure out what the trend is going to be. We can look at going from left to right across a periodic table. We can also look at going down a periodic table. So as we go from left to right across a periodic table, as we said, the effective nuclear charge increases. Since the electrostatic force is proportional to the effective nuclear charge, that means the electrostatic force increases as we go from left to right across the periodic table. So we can say it increases due to an increase in the effective nuclear charge. Along a column, we know that the effective nuclear charge doesn't change. But as we just mentioned, the distance between the nucleus and the valence shell increases. So that means that R is increasing. And since effective or the electrostatic force is inversely proportional to R, an increase in R means a decrease in the electrostatic force. So going down a column, we have a decrease in electrostatic force due to an increase in the radius. So overall, we can say that the electrostatic force increases as you go up and to the right of the periodic table.